Okay, so let's talk about the difference between two types of electrons that can be found in any atom. We have two categories. We have what are known as valence electrons and the core electrons. So the valence electrons, I think we met before, but just in case we haven't, by definition, those are the electrons that occupy the shell with the highest n value or principal quantum number value. All right. So the valence shell is where those electrons are located, right? So the valence shell would be the highest energy shell, and the electrons located within the valence shell are called the valence electrons. Now, it turns out that there is a correlation between the number of electrons in the valence shell and the group number for the main group elements, and this is only true for the main group elements. It's not true for the transition elements. All right. So basically, what you'll find is that the group number for the main group element, and it doesn't matter what the element is, that number will be valence electrons. So, for example, all elements in group 1A will have only one electron in its valence shell. All elements in group 2A will have two electrons in its valence shell, and so on and so forth. So that's basically what the valence electrons are. Valence electrons are the electrons that occupy the highest energy shell. Now, the inner core electrons, or simply called the core electrons, these are basically the electrons that are located in shells that are not valence shells. All right. So if you look at, for example, the electronic configuration of arsenic, which is shown here, right? You'll see that the valence electrons are the electrons occupying the highest shell, energy shell, which would be the fourth shell. So in the case of arsenic, you have a total of 5 electrons in the valence shell, all right? Whereas all other electrons will be the inner shell electrons. So these 10 electrons here, plus the electrons which are represented by this symbol right here, those electrons would be the inner shell electrons. And as you can see here, there's a total of 28 inner shell or core electrons present in the in the arsenic atom, all right? So it's very important that you understand the difference between these two, because understanding this will help you to understand how we can determine the electron configuration of ions. Now, what we're going to look at is how we determine the electronic configuration of anions firstly, and then we look at doing the same thing for cations afterwards. So in the case of the anions, it's very simple actually. All you have to do is determine the electronic configuration of the corresponding atom, and then you simply add the number of required electrons to get the corresponding anion. And basically, that's it. In most cases, it usually results in a complete shell upon the addition of the extra electrons, right? And typically, a non-metallic monatomic ion ends up with the same electron configuration as the nearest group 8 element in the same period, all right? So for example, in the case of the oxide ion, which is formed by adding 2 electrons to the oxygen atom, you're going to end up with the electronic configuration of neon, all right? In the case of the bromide ion, which results when you add 1 electron to the bromine atom, you're going to end up with the electronic configuration of krypton, okay? So that's basically how you determine the electronic configuration of monatomic anions from their atoms. Now, when it comes to determining the electronic configuration of cations, you have to basically remove electrons from the corresponding atom. And usually the atom would be a metal atom. You have to be careful, however, because the electrons that you're removing must be those electrons belonging to the valence shell first, right? And then if there's any more electrons to be removed from other shells, you do it correspondingly. So let me see here. Another thing here I should say here is that if you have 2 subshells within the same valence shell, then basically you start removing electrons from the subshell with the higher L value. All right. So for example, if you have electrons within a shell occupying s and p orbitals, then you start removing electrons from the p orbitals first before you start removing electrons from the s orbital. All right. So here are some examples. In the case of fluorine, to form the fluoride ion, you add an electron to the 2p sublevel here, and you end up with this electronic configuration, which is the same thing as the electronic configuration of neon. In the case of sulfur, this is the electronic configuration. To form the sulfide ion, you add 2 electrons to the 4 already in the 3p sublevel. You end up with this, which is, by the way, the same as the electronic configuration of argon. Okay, now that's as far as the formation of anions are concerned. Let's look at what happens when cations are formed. So here we have the electronic configuration of strontium, which is the electronic configuration of krypton in addition to 5s2. So when it forms a strontium ion, it results in the loss of these 2 electrons. So therefore the 5s sublevel will disappear and you end up with simply this, all right? So that's basically how you determine the electronic configuration of the strontium ion. In the case of the titanium atom, this is the electronic configuration. When titanium forms titanium 4 plus, it's going to lose these 2 plus these 2 electrons. Now, please note that these 2 electrons will be lost first, right? Because these 2 electrons are in a higher valence shell, and then these 2 electrons will be lost afterwards to form this. So therefore, you're going to end up with the same electronic configuration as argon. Here is the electronic configuration of iron. If you want to look at how the iron 2 plus ion is formed, these 2 electrons will be lost here because, as I said before, the 4th shell is higher than the 3rd shell. So the 2 electrons will be lost here, and therefore the resulting electronic configuration of Fe2 plus will be this right here, Ar3d6. All right? So remember, it's the valence electrons that are lost first, and then other electrons next in line in terms of energy will be lost afterwards. So based on this, we should be able to answer these 2 questions. What would be the configuration of Fe3 plus? Well, for Fe3 plus, we can basically start from here. All we have to do is remove an electron from here. So therefore, the electronic configuration of Fe3 plus is going to be, for Fe3 plus, is going to be the electron configuration of argon, 3d5. All right? So that's basically how that is done. All right? Now, the next question here being asked is, what is the electronic configuration of tin 2 plus? Now, in order for us to do that, let me go to another PowerPoint. Let me create another slide here. Let me take this out. Let me take this out. Now, in the case of tin 2 plus, the electronic configuration, whoops, let me do this here. The electronic configuration of tin, well, let me see what the atomic number of tin is first. Okay, where's my table? Tin has an atomic number of 50. So the atomic number of tin, whoops, is 50. All right. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So that's 40. Okay, now I need to recall, or let me, I'm sorry. I made a big mistake. Let me go back and do this again. 10, and then atomic number 50. So as I said before, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and I'm trying to remember now. So after 3d, you have 4p, so that would be 4p6. And then after 4p, hold on, let me see here. So this is up to here is 30, 36. So after 4p6, what do we have? We have 5s2, 5s2, so that's 38. After 5s2, we have 3d, hold on, we have 4d10. So that's 36, 38, 48. So the next orbital is 5p. So that would be, okay, why did that happen? Five P2. Okay, so that's a full electron configuration of tin. So to get tin 2 plus, basically we're going to lose 2 electrons. So that means this orbital will go. So basically the rest of this would be the electronic configuration of tin 2. And in order for us to determine the abbreviated version, the group 8 element that precedes tin will be, according to my periodic table, krypton. So the electronic configuration of krypton would be represented by 36, which would be everything up to, this is 30, everything up to here. So all of this right here will be krypton. So that would be krypton. And then you have 5s2, 4d10. So this would be the electronic configuration of the 10-2 plus ion. Okay, so keep that. Go back to my slide here. Okay, so that's basically how we determine the electronic configuration of ions. Now, oh, here's another example. So let's look at this example here. Write down the electronic configuration of cobalt 3 plus in a noble gas abbreviated SPDF notation. So let me do this. Let me do this. Let me go here. Okay, so cobalt, according to the periodic table, the atomic number of cobalt is 27. So cobalt is 27. So the full electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. All right. Make sure I'm doing this right. This is 2 here. Okay, so that would be the full electron configuration. Now, the abbreviated version for this would simply be, well, the group 8 element that comes before cobalt will be argon. So it's going to be Ar, which represents all of this here. And then 4s2, 3d7. All right. So for the cobalt 3 plus ion, remember now you start removing electrons from the highest valence shell of the atom. So that means that you're going to lose these 2 electrons here. So this subshell will disappear. And you're going to lose 1 from here. So the resulting electron configuration of cobalt 3 plus would be Ar 3d6. All right, so that would be the electron configuration of the cobalt 3 plus, the abbreviated version. Okay, so much for that. So one last thing in this particular video I want to talk about is in reference to the magnetic properties that are displayed by elements. Now, in this regard, there are 3 types of magnetic properties. You have diamagnetism, which is the weak repulsion that's associated with paired electron systems. And then you have paramagnetism, which is the attraction that's associated with unpaired electrons. And please note that this particular effect is much stronger than diamagnetism, right? This is one that it can be more easily observed. And then you have ferromagnetism, which is an exceptionally strong attraction that certain elements will have. Iron is one of those elements that displays ferromagnetism and a few other substances. Our focus for this discussion deals with paramagnetism because it's associated with the presence of unpaired electrons. So basically, any particular element that has in its structure, in its electronic structure, unpaired electrons will display paramagnetism. And one can determine these magnetic properties by weighing a substance in the presence, weighing the particular substance in the presence and then in the absence of a magnetic field. And this diagram here basically demonstrates this. So here we have, let me get to my pointer here. So here we have your substance that you're trying to determine its magnetic properties. There's no magnetic field which you have to turn on. Usually this is connected to some external circuit where you turn on the switch and it generates a magnetic field, right? So you weigh the substance before you turn on the field. And then when you turn on the field will have an attraction for the substance if the substance has a particular magnetic property. And then as a result of that, you can determine the difference in mass as that you'll be recording here, all right? So it turns out that the mass may have increased or appears to have increased because the substance in this case would be paramagnetic, right? Because it will have unpaired electrons, all right? Anything that has unpaired electrons is paramagnetic, right? So that's basically how that is determined. So we can use that idea to answer this question. It says a sample of chlorine gas is found to be diamagnetic, right? Can this gas sample be composed of individual chlorine atoms? Well, in order for us to answer that, we have to look at the electronic configuration of chlorine. And if you look at the electronic configuration of chlorine, you'll see that, well, chlorine firstly has 17 electrons. So therefore, its electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p5, right? Now, within the 3p sublevel, you have 5p orbitals, and this is how the electrons will be distributed among them. 1, 2, 3, 4, 5, right? So what that tells us is that because we have unpaired electrons here, this tells us that the chlorine atom is paramagnetic. But we know, according to the information here, that chlorine gas is diamagnetic. So what that indicates is that the chlorine gas is not made up of chlorine atoms, and we now know that chlorine actually exists as Cl2, all right? Therefore, it is a chlorine molecule which is diamagnetic, because if we were to determine the electronic configuration of the chlorine molecule, you'll see that it has totally paired electrons, no unpaired electrons, which we won't get into at this chapter, all right? So it turns out that the chlorine atom itself is paramagnetic and the chlorine molecule is diamagnetic. Okay, we're going to stop here. The next thing we're going to discuss are trends in periods when it comes to the different elements in the periodic table, and we're going to see how that relates to their electronic structure. Okay, until next time.